welcome back. So in this other video we'll continue my series on the Covenant starting session. Let's share the screen. Okay, so as already mentioned in the other videos of this series, I found out this website called Bitcoin Covenants Wiki, and they have these two sections, and well, there's additional reading, which is also really important, and the great script restoration in particular. So as we have already seen in the other videos, studying this topic is not a linear path, doesn't have a linear path. At least the one that is working for me is more a cyclical path, in which I started from a use case, the transaction templating, for example, and after understanding the transaction templating generalization, I explored the proposals which would allow to implement it in the blockchain. Therefore, going to these proposals, I had a look at this. So CTV, any prev out, and TX hash. Then I also explored a bit CATT, which in the Bitcoin Covenants Wiki public website is not available. However, you can find the correspondent page in the GitHub of this website. Then, yeah, like for any prev out, I had a look also at what will be the use cases in which it will be useful. I did the same for CTV. I explored the BAPs, the PR reviews, and then I confronted the three of them, especially any prev out versus CTV and TX hash versus CTV. And now I have a superficial basic understanding of these topics. Therefore, today I will continue with this same approach. In particular, I will explore first of all the idea of vaults, which is something that CTV in some way enables. OP vault. Okay, didn't know that it exists. However, let's go and let's see what vaults are. I have an intuition, but let's see the definition they have here in Bitcoin Optech first. Okay, therefore, as we can see here, vault are a type of covenant that require two separate transactions to appear in two different blocks in order for a user to spend money from their wallet. The first transaction signals that someone is attempting to spend the money and gives the user a chance to block the second transaction that completes the spend. A vault protocol specifies a minimum amount of time or number of blocks that must pass between the two transactions, giving the user that amount of time to notice if someone stole their private key and is attempting to steal their money. If the user detects the theft attempt, most vault designs also allow the user to either send the money to a safe address that uses a more secure script, or to permanently destroy the money to prevent the thief from profiting from their attack. Some vault designs rely on covenants that require consensus changes to Bitcoin. Other vault designs use existing protocol features plus techniques such as signing transactions long in advance of needing them and then destroying the means to sign alternative transactions, either by securely deleting the signing key or by using multisig to ensure multiple independent keys will need to be compromised. Okay, therefore the first important thing is for me is that Vault have designs which involve covenants, but there are alternatives with the current state of the blockchain, Bitcoin blockchain technology protocol, let's say, instead of technology. And then we have several ways when speaking about implementations which rely on covenants. We have also different techniques. So here we have some links talking about vaults, and here we have some primary code and documentation. I'm not sure if it's all the same source or it's like different implementations. Okay, so these two guys wrote this article which is about Bitcoin security vaults. How do you store your bitcoins? Sure, the coins are registered on the blockchain, but how do you store the private keys that secure your funds? If you don't have any bitcoin now, how will you keep your private keys, the small files that have direct monetary value, safe from both loss and hackers? Given that key security is one of the major obstacles to mainstream adoption of cryptocurrencies, and every single coin hacking event is a black eye for the entire cryptocurrency community, a lot rides on the answer to these questions. Ask any cryptocurrency veteran and they'll tell you that you need to create the keys using well-written software and true sources of randomness. And they'll tell you to use multisig to divide up your keys such that hackers need to break into not just one but multiple machines to gain access to your funds. And such safeguarding is quite difficult. The conventional method to keep private keys safe is to follow a 37-step operational security guidelines. What? Didn't know about this specific number of steps. That involve air gaps, dedicated laptops, and epoxide ports. But what kind of internet currency needs to be kept on an air gap dedicated laptop, potentially in a pyramid with false burial chamber? It's no wonder that mere mortals often opt out for this decision by trusting a large exchange to keep their coins. Of course, that just outsources the problem to that exchange's security, which faces exactly the same challenges, only with much higher stakes. The fundamental trade-off between availability and security means that regular users face a difficult decision. At the extremes, one either stores the keys on multiple devices where they are vulnerable to theft or keeps a single encrypted copy in an air-gapped secure storage, which the user needs to visit to reconnect to the internet ever so briefly and recite a full paragraph password to recover the password. As a result, cryptocurrency archives are full of sorry for your loss events where coins were lost by mistake or where hackers stole private keys and go away with substantial sums. This happens to savvy users too. A colleague, a CS graduate student who was an early Bitcoin miner, lost around 10,000 coins. Another friend shows a very good password. It was so good that he could not recall it after a couple of years. Even with the help of hypnosis and brute force attacks on his password choosing strategy. Overall, our computing infrastructure is nowhere near safe enough for storing high-value assets. Bitcoin has become a universal bounty, where hackers break into machines and immediately reap financial rewards. What we need is a way to lock up coins in a way that it is impervious to hackers and thieves. Bitcoin vaults. At the Bitcoin workshop in Barbados, Malter Moser will present our solution to Bitcoin private key management problem. Specifically, our paper describes a way to create vaults, special accounts whose keys can be neutralized if they fall into the hands of attackers. Vaults are Bitcoin's decentralized version of you calling your bank to report a stolen credit card. It renders the attacker's transactions null and void. And here's the interesting part. In so doing, vaults demotivate key theft in the first place. An attacker who knows that he will not be able to get away with theft is less likely to attack in the first place, compared to current Bitcoin attackers who are guaranteed that their hacking efforts will be handsomely rewarded. Okay, this sounds really cool actually. I didn't know anything about vaults. Operationally, the idea is simple. You send your money to a vault address that you yourself create. Every vault address has a vault key and a recovery key. When spending money from the vault address with the corresponding vault key, you must wait for a predefined amount of time, called the unvaulting period, that you established at the time you created the vault, say 24 hours. When all goes well, your vault funds are unlocked after the unvaulting period, and you can move them to a standard address and subsequently spend them in the usual way. Now, in case Harry the hacker gets hold of your vault key, you have 24 hours to revert any transaction issued by Harry using the recovery key. So his theft essentially gets undone, and the funds are diverted unilaterally to their rightful owner. It's like an undo facility that the modern banking world relies on, but for Bitcoin. Now, the astute reader will ask, what happens when Harry is really good and he lies in wait? He lies in wait to steal not just your vault key, but also your recovery key. That is, he has thoroughly pawned you, and as far as the network is concerned, is indistinguishable from you. Vaults protect you even in this case. The recovery keys have a similar lock period, allowing you to perpetually revert every transaction Harry makes. Unfortunately, at this point, Harry can do the same and revert every transaction you make. To avoid a perpetual standoff, the recovery keys can also burn the funds, so no one gets the money. The upshot is that Harry is not going to be able to collect a dime of proceeds from his theft, and this in turn means that Harry is unlikely to target Vault in the first place, because there is no positive outcome where he gets to keep the proceeds. Okay, so building vaults on Bitcoin Covenants. Implementing the vault mechanism in Bitcoin is far from trivial. One could implement a special purpose facility just for vaults. with special address types for vault addresses, many new opcodes and the like. But we believe that architectural changes should be both minimal and general. We therefore propose a simple change to Bitcoin called Bitcoin Covenants. As in legal covenants, a Bitcoin covenant checks a condition depending on a transaction. In a sense, a covenant is a restriction placed on the shape of a future transaction. Because covenants can be recursive, they can self-perpetuate or they can be limited in time, allowing one to implement a range of rich semantics. The idea to extend the power of scripting language isn't new. In fact, we took the name Covenants from an old tongue-in-check post by Greg Maxwell that suggested an unlikely mechanism and asked for preposterous use cases. It's a recommended read. Fungibility is not affected. It's critical to note that vaults do not affect coin fungibility or the irreversibility of regular transaction in any way. Vaults are a personal defense mechanism. You take the money that you want to keep safe and put them in a vault address that you create. Call it V. In doing so, you give up the ability to spend them quickly in return for theft prevention. When you want to spend the coins, you unvault them from V into your hot wallet, W, and you pay a merchant, M, from W. Only coins in your possession can be vaulted, and they can only be unvaulted back to your possession. You can trick someone into accepting a vault payment and then take the coins back. The entire design revolves around personal protection for chosen coins in one's possession, without disturbing any of the rest of Bitcoin's properties. Overall, our suggestion is a simple yet powerful addition to the scripting language that is easy to reason about and opens the door to a variety of constructs. Vaults are one of the first use cases of Covenants, a solution to a problem that has perennially plagued every Bitcoin user ever since the first day of the system's release. We hope that vaults will make it easier for people to safely keep their funds online, knowing that they can always undo a theft and, more importantly, to deter the thefts in the first place. Okay, so Malte Moser. Okay, so this is the paper. Let's see, it's a 16 pages paper. This has been published in 2016. Interesting. So I think I will read this. Oh, sorry. So I'm interested in the first note. So this is introduction. Let's see where he's using. So it's not one. instances are the context of baked sidechains and proof of stake. Okay, so I'm interested in going deeper on this paper. Covenants in Elements Alpha. Below is the script pub key for the main vault. It can be spanned by the following script sig, which initialize the stack in reverse order. Then vault loop script. Wow, I'm really curious about this use case actually. It looks to me that this is a really good way to store your coins. Nice. For sure I will go through these two. So, okay. First of all, we achieved the current goal of this video, so we understood something more about the use case of vaults. Okay, so these other guys proposing a way to implement vaults which doesn't require a soft fork. Okay, so this also is something that has been published after the paper we have been through. Okay, this is also really cool and interesting, because the idea I'm having now, inspired by these works, is that it will be a really cool way to explore script and opcodes by experimenting with these techniques. Those who those which do not require covenants first, and of course I would love to also think about the version with covenants and be able to try. So this is exciting. Okay, custody protocols using Bitcoin vaults. So 2020 Cornell University, which is the one involved in the original paper. So what's saying here? Cryptography secure custody protocol using Bitcoin vaults. Sorry, it's so small, everything. So a Bitcoin covenant is a mechanism to enforce conditions on future Bitcoin transactions. This paper demonstrates how to integrate a Bitcoin vault into a custody protocol and demonstrate the security properties of a protocol. Wow. Finally, the architecture employs a detection and response system that enables fail-safe recovery from attempted or partial deaths through a second type of covenant transaction, a push-to-recovery wallet transaction. So cool, so there's a lot of method here. From Jacobs, Wamba, MCSI. Wow, he did a really cool work. What's his face? Okay. Nice. Okay, then we have some citations in the newsletter. So let's have a look at one thing. Okay, so I'm asking LLM to clarify me the differences between non-covenant solution and one using CTV. So Bitcoin vaults overview. Vaults are designed to mitigate theft risks from compromised key by introducing delayed withdrawals, enabling pre-programmed recovery paths, and separating cold, hot, and recovery paths. The vault designs attempt to make unauthorized theft time-consuming, offering the user a chance to intervene. Non-covenant vault techniques. These use existing Bitcoin script capabilities, and a common design includes unvault transaction with a time lock, recovery path using pre-signed transaction that can be broadcast in case of suspicious activity, key components, pre-signed transaction stored securely, use of unlock time CSV to delay spending, multi-sig for further control. The pros are deployable today, no consensus change required. It's flexible with creative scripting. Cons, the cons are operationally complex and fragile. Secure storage of pre-signed TX is hard. Vulnerable to key compromise if attacker gets both spend path and recovery transactions. Non-composable, difficult to nest or generalize these vaults. Instead, when we're talking about CTV-based vault techniques, so CTV is a limited form of covenants, allowing outputs to restrict what future transactions can look like. So vault UTXO commits to a specific unvault transaction structure using OPCTV. Recovery and withdrawal paths encoded on-chain via covenant logic. Spending must follow predetermined tree of spending transactions. Pros are stateless security, no need to store pre-signed TX transaction. Its composable and provable structure enables recursive vaults. More robust and audit friendly. Cons are it requires soft fork and less flexibility than for recursive covenants, like more expressive covenants proposals. So, non-covenant vaults are an impressive feat of creative engineering, but they are workarounds with real operational risks. CTV-based vaults, though more limited in expressiveness, elegantly solve many of the core problems by shifting enforcement on-chain in a secure, auditable, and stateless way. However, CTV requires a soft fork, and there is still debate around its activation. But for secure, scalable vaulting, CTV is a strong contender and enables future innovations like recursive vaults, delayed inheritance, and spanning trees with pre-committed policies. So, okay, it's clear to me the key difference. An upvolt code and the related consensus changes that, if activated in a soft fork, would add support for vaults. Unlike vaults possible today with pre-signed transactions, vaults aren't vulnerable to last-minute transaction substitution attacks. Vaults are also batched operations that make them more efficient than most proposed design that only use more generic covenant mechanism. Okay, so let's see this BIP. Sorry, by beeps. Okay. So 345 by James O'Byrne and Greg Sanders. Greg Sanders, it's a name which I already have seen somewhere. BTC. Two new TypeScript opcodes that add consensus support for a specialized covenant, opvault and opvault recover. These opcodes, in conjunction with object template verify, allow users to enforce a delay period before the signed coins may be spent on an arbitrary destination with the expectation of a pre-specified recovery path. At any time prior to final withdrawal, the coins can be spent to the recovery path. Okay. When is this from? 2023. So the evolution of the discourse arrived at this point where we have some specific opcodes that, in combination with opctv, would allow to implement these techniques directly. Now, vault are a type of covenant that require to separate transaction to appear in two different blocks in order for a user to spend money from their wallet. The first transaction signals that someone is attempting to spend the money and gives the user a chance to block the second transaction that completes the spend. A vault protocol specifies a minimum amount of time or number of blocks that must pass between the two transactions, giving the user that amount of time to notice if someone stole their private keys and is attempting to steal their money. If the user detects the theft attempt, most vault designs also allow the user to either send the money to a safe address that uses a more secure script, or to permanently destroy the money to prevent the thief from profiting from their attack. Some vault designs rely on covenants that require consensus change to Bitcoin. Other vault designs use existing protocol features plus techniques such as signing transactions long in advance for needing them and then destroying the means to sign alternative transactions. Okay. Okay, so this is a really good use case. Upvolt and upvolt recover. Okay, so these are proposals which work in conjunction to check template verify, and they allow users to enforce a delay period before designated coins may be spent to an arbitrary destination, with the exception of a specified recovery path. At any time prior to the final withdrawal, the coins can be spent to the recovery path. This proposal is explicitly aimed at enabling the vault's use case. So there's also a PR referring to the BIP which we have seen some minutes ago. And this is the code. Oh no, but well, okay. Whatever. For use cases that are enabled by CTV, we refer to the more general use case page of transaction templating. So let me understand, why do we need CTV? So, sure, let's break it down in simple terms. I want to understand why upvolt and upvolt recover still need CTV. I mean, it's clear to me that they are not sufficient in some way, but I want to understand which are the details where CTV is necessary for them. These are Bitcoin script operations designed to create a vault, a way to store coins so that they can't be spent instantly, giving you time to react if someone tries to steal them. They work like this. You lock your coins with a rule: you can only spend these coins after a delay like 3 days unless you use a special escape hatch, the recovery path. If someone tries to steal your coins, you have that delay window to use the recovery path and save them. So why do they need object template verify? CTV is important because it allows you to lock it exactly what the next transaction will look like. That way, during the delay period, no one, not even you, can change where the coins are going or try to cheat the vault. Here's the key point. Upvolt defines that the coin can be spent after a delay, but without CTV, you can't enforce what the future transaction will look like. So with CTV, you can say after 3 days, the coin can only go to this specific place, no funny business. Why not just use OP-Vault alone? Yeah, so this was my question. Without CTV, we would only delay spending, but wouldn't control what happens after the delay. So an attacker could still try to redirect the coin somewhere else once the delay is over. OP-Vault enforces a delay. CTV enforces what happens after the delay. Together they make a secure vault. Okay, therefore OP-Vault without CTV would work only with a pre-signed transaction, right? They're inflexible. If you want to change where the coins go later, you have to make a whole new vault and pre-sign again. They're fragile. If anything about the transaction changes, like a fee rate or UTXO, it breaks. They're hard to manage securely, especially for many users of wallets. Okay, so OP-Vault, it's basically useless. So yeah, I mean, why OP-Vault? Why creating an operational code? It may, in the superficial knowledge, with the superficial knowledge I have until now, CTV alone can also implement a certain form of vault, but let's see why it's still proposed. So okay, so is OP-Vault useless if we already have CTV? Not quite. You're correct that CTV alone can be used to build vaults. In fact, many early vault proposals did exactly that using CTV. So why even OP Vault? Let's break down what OP Vault adds on top of CTV. What OP Vault, so native delay mechanism. OP Vault adds a built-in time delay enforced by the script between when the user initiates a withdrawal and when it can be finalized. With CTV alone, you have to manually encode this behavior using transaction trees or complex script logic. Okay, so built-in recovery path. OP Vault allows a recovery transaction at any time before the delay completes. With CTV alone, you can simulate this, but it's more complex and requires more script gymnastics or multiple preassigned paths. Statefulness and compactness. OP Vault is more compact and expressive. Instead of constructing complex tree structures of CTV commitments to mimic state transactions, OP Vault encodes that behavior natively. This makes wallet implementation easier, vault structure more auditable and verifiable, on-chain data smaller and more efficient. User friendliness and safety. With OP Vault, you don't need a complex template tree or transaction preassigned logic. It's more plug and play for wallets and reduces implementation mistakes. Okay. Now, why CTV? There are opcodes like tix hash with tix id selector, which give the users more granularity on the transaction templating is wouldn't that be a better solution? Why OP Vault is being proposed specifically with CTV. You're clearly thinking, fuck you, GPT. Let's look at why OP Vault is tied to CTV, even though there are more expensive alternatives that offer fine-grained control. So simplicity and safety over flexibility. CTV is intentionally limited. It commits to the entire structure of the spending transaction. This makes easy to reason about, hard to misuse, and safer for critical applications like vaults. Vaults are safety feature, not an expressive smart contract. So the design philosophy is do one thing very securely and very simply. OP Vault plus CTV is a very narrow auditable pipeline where coins can only go from vault, delay, destination, or vault, recovery. No extra complexity. Opcode transaction hash is more powerful but also more complex and risky. Commitments, it's strictly more expressive. It allows commitments to only parts of the transactions, far more customizable templates. But that flexibility makes script harder to audit, introduces more surface area for bugs and unexpected behaviors. Could lead to dangerous interactions, especially if used improperly in vault setup. In contrast, CTV is minimal. This output can only be spent in this exact way. That makes it ideal for vault enforcement. CTV already exists as a mature BIP. From a process standpoint, CTV has been implemented, tested, and simulated for years. It's simple to verify and has known behavior. Vaults can be implemented and deployed today with just CTV. Instead, OPTX hash might come later, and in fact, many advocates support eventually enabling both, for Bitcoin community tends to favor small incremental changes. Yeah. Is CTV tested on liquid? No, CTV is not implanted in liquid. However, liquid, which is built on the Elements code base, has its own set of Covenants opcodes. Okay, but then where has been tested CTV? Bitcoin Core custom branches. CTV was first proposed by Jeremy Rubin, blah blah blah, and implementation was submitted as pull request to Bitcoin Core. It's not merged into Core. Signet and Testnet. CTV has been activated on custom Signet and Testnet networks. Projects like checkandplayverify.com run public Signet networks with CTV enabled, so developers could try it out. What? Wallets are tooling were created to work with CTV on this testnet. Simulators. Tools like Miniscript, BitMax Research, Covenant Simulator, and custom vault design in sandboxes. Does this even exist? Looks like invented. My friend is hallucinating. Yeah. So I can't really trust this LLM. However, I think that the first part, the confrontation, makes sense. It's something that was on my mind, and seeing it written is just, I think, it's a good way to confront them. So now I'm really tired, and I think I will interrupt here this video as we cover the good use case and proposal. Therefore, now we incremented the amount of things I have to read. I think that now we will close the video and dedicate some time to reading. So next time I will be more prepared. Maybe I will go faster, will have more ideas, or maybe more doubts. Because while studying and reading good material, normally I have a lot of doubts emerging about my knowledge, but also curiosities about new things, new points of view I acquire. Therefore, see you in the next video. Thank you for being here another time. I hope to see you next time again.